just a short overview I will give because most of the items is already covered by Dr. Kumar. So here my primary focus will be on how the analytical methodology will be applicable for radiation and along with other mode of heat transfer combined conduction and convection radiation. So before you can start this, so let me just give you a brief overview. Just short overview. Like radiation participating video, which you are already aware of. Dr. Kumar has already made this part. And then we'll see some mathematical similarity between our conventional CFD problems based on convection diffusion system and our radiation transfer case. So all these similarities needs to be looked at so that the appropriate numerical methodology can be applied for the outcome, which looks little different mathematically. Of course, the approach is also different, but how our existing CFD techniques can be applicable for solving this unique equation of radiation transfer that will be discussed here. Then some of the existing methods I will be talking about, like flux method, then the discrete ordinate method, which is quite popular since the beginning, and then comes the finite value method. And later on, it was realized that all these methods, whatever existing, so these are all can be derived from this finite value methodology. So the basic background framework, what is required for solving different transport equations using the radiation using finite value method, that will be our primary focus in this short lecture. So then we will cover some introductory part of radiation with other mode of heat transfer, and that's our concluding class. So coming to radiation participating video. So this is your RP, which you are already aware of. So I have given the total RP including the transient part. So transient part sometimes is applicable for ultra short time scale applications. Like here you can see this has significance in ultra short time scale phenomena, because you see the denominator term, that is term called c, which is the speed of photon travel. So which is the light speed. So you know how fast the light moves in the medium, right? So then if the time scale of our observation is not so small, then we cannot visualize any transient effect on photon transfer. So that's why it has only significance you can find in ultra short time scale phenomena, like if you go sub nanosecond or picosecond phenomena, then this term is quite play a major role, like some kind of laser applications also. So then comes our other means what are the phenomena going on, which is already being covered by Dr. Kumar, like absorption and outscattering. Because absorption, emission and scattering, these are the three fundamental phenomena which we have been, based on which this radiating energy balance equation have been important. And this is for a particular pencil of photo ray, right? And then we'll cover this. Another is the emission, because sometimes the medium may emit also. So the emission is an augmentation term, so that's why it is prefixed with plus. And this emission is particularly based on temperature of the medium. So any temperature above absolute 0 Kelvin, the medium is ready to emit, right? And then the last term, which is the most critical term in RT. If this would not have been there, then handling this situation would have been quite easier for us, because then it will be just an ordinary differential equation. So this is the in-scattering term, which creates a lot of trouble, and then because of that, so many methodologies have been developed. So this is the in-scattering term. In-scattering term basically it refers to let the photon coming from all other directions into your direction of travel of interest, that will contribute. So that's why it is an augmentation term. So it increases the photon intensity, because whatever outscatter from other point of the medium which will come into your direction of interest, so that will add as a in-scattering term. What is the S? S is the direction. S is the particular direction, because this radiative energy balance equation, what you see, that has been developed for particular pencil of ray, means bulk of photon moving in particular certain direction. Okay. Then comes your flash method, the CDRT similarity. Because before we handle this complex integral differential equation, we have to see the similarity between conventional CFD techniques, which is applicable for solving like your diffusion as well as convection problems. How we can handle the integral differential equation using that CFD concept, which is valid for convection diffusion system. CD stands for convection diffusion system. So you can see that the convection diffusion equation, this is shown in for two-dimensional system. So here the first term is our transient, local transient phenomena term, and the second term is your convection term. Then the right hand side, the diffusion term and the source term as there. So if you look at the RT also, it looks very similar mathematically. Like it has a transient term, right? And it has this convection like term, although there is no convection like, because there is no flow, but there is a convection like term is there, and then you have a source term you can see. So this similarity you can find, like we can make this transient term of RT is very similar to your convection diffusion transient term, right? At least in similar form. And if you see the convection term in our original heat transfer fluid flow problems, which is quite mathematically similar to our RT, that is quite the spatial gradient of the intensity in different directions. So where this mu and z refers to our direction cosine, that I will show you later in subsequent slides. And then we do have a source term like this. So this source term, if you see that S is also can be similar format like minus beta I plus S, what have been found in RT. So this S is actually, it can be a nonlinear source for our conventional heat transfer fluid flow problem that can be written from, that can be linearized in the format like there is a constant part of the source term and there is a linear format of the source term S. So if you compare this SC plus SP5, then it is very similar to like your SP can be, now you can say it is nothing but minus beta, which is beta is the extinction coefficient, right? And then source is our radiative source, which consists of our emission term as well as our in-scattering term. And if you see the similarity, like there we are calculating the temperature for our conventional fluid flow heat transfer problems, and phi refers to our temperature, and here phi refers to temperature or any kind of enthalpy, spacing, whatever, depending on type of problems what you are daily, and here it is only the radiative intensity. So what is our observation from this mathematical similarity? What you can see, like there is no diffusion like term in RT, that means we can set this gamma, the diffusion coefficient, to be 0 for RT. So that is of course simplifying our problem by solving the RT. And looking at this mathematical similarity, so we can apply all the basic principles of developing any good numerical methodology for solving these kind of complex transport equations. So that rulers of CFD, whatever solution methodology so far have developed or people are trying to improve upon different methodology, they are solely based on this conservativeness property, then boundedness property, and then transportiveness property. So conservativeness means any kind of conservation principle can be applied. Conservation of energy, mass, momentum, like this. And boundedness means the solution must be bounded. Means solution should not shoot up. Means it should not be unphysical in its, while we simulate, it should not give us any unphysical results. So that's why we, while developing a numerical methodology, we must ensure that the method should be bounded. Means the result should be physically plausible result should be predicted from the numerical method. And another is transportiveness. This transportiveness feature is something like, let's say the transportiveness feature means some flow kind of phenomena. Transport means something is flowing. So here, like in our conventional fluid flow heat transfer problem, the flow is happening. The heat is flowing because of the actual flow in the field, like U and V component in your convection diffusion equation refers to the flow field. And here, this transportiveness feature you can find in our mu and j, which are called direction cosine, in which direction the photon will also travel. But of course, for U and V, you have to compute in your flow field the momentum equation, but here you do not have to, because these are fixed values, because you have to predefine your direction, in which direction you want your photon to travel. Okay, so that's why this mu and j is a simplified form of our convection diffusion equation with a constant velocity. A prior you know the flow field, then you want to predict the temperature distribution. So these three features are quite valid to develop a methodology for our radiative transfer equation. Then coming to the flux method. So that is the very first method, long back in 1970s time people have developed this flux method. So this actually simplifies the original problem to much extent, because in original format it is quite complex, because you can see the actual radiant intensity distribution is like that. So there is intensity, these arrows what you see, these are all different bulk of photons going in different directions, right? And their intensity magnitude, their length basically defines the intensity magnitude, right? So lower length means short arrow means quick intensity. Larger size arrow means larger quantity of photons are traveling in that direction, high intensity. So in different directions you have pretty very unstructured format it is there, right? But what the flux method does is that and this intensity distribution is spherical in nature. Means in the total sphere in different directions, how the intensity varies, that has been shown in the left figure. And in one hemisphere you have uniform intensity, and in the other hemisphere you have also uniform intensity of different magnitudes. So that means basically we have two magnitudes of intensity in two different hemispherical directions, right? So that can be shown here, like I is your here. You can see this I is I plus for positive coordinate direction and I minus for negative coordinate direction. And for positive hemisphere we have this, the radiative transfer equation can be written like this, because radiative transfer equation for positive hemisphere, since it has to be integrated, then after integration you will get this kind of an radiation. So for positive hemisphere as well as for negative hemisphere I minus. Okay. So the first method, what is our observation is that it divides the angular space into two solid angles, and the magnitude of the radiant intensity is assumed constant in each solid angle. That is what you can see in this figure, like all the intensity in this positive hemisphere or negative hemisphere is constant here. Magnitude of intensity is constant. That's why it comes, right? And this approach reduces the RT to two ordinary differential equations, which can be solved using any convenient method. And what is our remarks on this method is that the method would not accurately model anisotropic scattering. Anisotropic scattering means the scattering in different directions are different, depends on in which direction bulk of photons are moving, what quantity, that is defined by that is not uniform throughout the spherical distribution. So with two solid angle discretization practice, it is very difficult to capture anisotropic scattering. Then comes our U method, that is our discrete coordinate method. So since people have faced this problem to address the anisotropic scattering, they look for any alternative methods, and then one of the very well-known Indian scientist Chandrasekhar, during his research in USA, he developed this discrete coordinate method. So the actual radiant intensity distribution is looking like this. And on the right hand side figure you can see that the discrete coordinate method approximation is that in every coordinate direction you can pick the intensity and solve for it. Then you will get the actual magnitude of the intensity. So discrete in nature. So the discrete nature of photon travel can be very well captured using discrete coordinate method. And for RT, how we can write using discrete coordinate method? It's same like this. The L stands for different directions, like this, discrete direction. And this part is your in-scattering part, where this WL is the quadrature set. So different directions, we have to satisfy certain moment principle to find those different weights in different directions. So that is the primary focus of the DO method. And what are the features? Features is that there is no solid angle reference in discrete coordinate method, because there is no concept of solid angle in discrete coordinate method. And the angular direction can in principle be chosen early. And the quadrature sets the ordinate directions and angular weights associated with it can be developed and integrate the radiating energy and in scattering terms accurately. So that weights have to be found out. So people have that data set is available for different quadrature sets for different ordinate directions. And then using those tabulated data you can simulate the in-scattering. And the remarks what you can get from this discrete coordinate method is that the accurate calculation of several discrete angular rates satisfying the full half-range moments are computationally challenging for certain configurations. Let's say if you have a complex configuration, then this finding those angular quadrature sets are quite computationally intensive. So that limits the applicability of this method for certain situations. And then comes our finite volume method. So what it does? It completely removes that requirement of finding the angular quadrature sets, what is there in the discrete coordinate method. So this finite volume method, so it is quite a popular method for solving CFD problems. So those, have anybody been exposed to CFD earlier? Very good. So then you can easily understand the methodology what we will be discussing about. But for a beginners also, I tried my best to explain the things. Some of the things, if it is not there, I will share it with you. Very important. So the domain discretization using control angles, the angular space, because in radiation you have a, along with the spatial domain, you have an angular domain also there, right? Because photons are traveling in different directions. So that directions have to be, direction domain have to be taken into account, like our azimuthal angle and our polar angle. So total azimuthal angle is 2 pi and total polar angle is pi. That constitutes the full sphere, whose value, solid angle value will be 4 pi. And the control angle, control volume for geometrical space, which is quite extensively used for our conventional CFD related heat transfer problems. The calculation of angular weights as required in QA is avoided here. It is completely you can avoid in calculating any directional weights, because we have developed the concept of control angle, and based on that we can easily compute our equivalent angular quadrature sets based on our distribution of angular space. It is based on conservation. The central idea of getting this finite volume method is popular because it is based on conservation. So you can easily check the methodology's performance by looking at the quantity what you are measuring, whether it is conserved at any arbitrary spatial location. So that is the beauty of this finite volume method. And then we have to have a concept of control angle. So that control angle is shown here in this figure. You can see, like, this is our control angle, and that can be calculated computationally like this. There is a mathematical expression, sin theta d theta will be pi, and then after integration we get this expression. And theta and phi are our theta is the polar angle and phi is the azimuthal angle. Azimuthal means this one and polar means like this one. Okay, that constitutes the full sphere. So the polar angle span is 0 to pi and the azimuthal span is 0 to 2 full circle. Okay, then you can constitute the sphere. So you can create your control angles as per your requirement, or as per your requirement in the based on your geometrical set. That is quite flexible here in developing the control angles using finite volume. Then the actual intensity. Then we will see that how a VM will take care of the actual intensity distribution. The actual is this one, but then FVM when we will apply different control angles. So in each of the control angle, the magnitude of intensity remains constant. So then depending on your actual intensity distribution, the more number of control angles you create, the more distribution of intensity you will get. So you can resemble the actual intensity distribution quite easily using finite control angle generation practice. Okay. Like here I have shown you one of the figures. Here the number of control angles are 1, 2, 3, 4. 4 control angles have been shown here. So in each control angle we have a different intensity distribution. So if you are expecting that there will be large variation in intensity in different directions based on your boundary conditions, then you can create more number of control angles. That is the flexibility you do have. And the two-flux method is something like you can now say that two-flux method is the subset of finite volume method. It is a special case of finite volume method where you have only two control angles, right? Two hemispherical control. If in a finite volume method you are generating two control angles, then it is nothing but a flux. Okay, so that has been shown here, and that discrete ordinate method also can be obtained from finite volume method in the sense in each discrete direction is captured using a control angle and you integrate that control angle with a delta function. Means within this control angle in a particular direction only the intensity is available, in other direction within that control angle it is not available. So that if you apply that principle in your finite volume method, it will automatically give you the result of U, right? And intensity is assumed within a control angle. That is our primary features of the finite volume method. And then you integrate this equation because it is based on conservation principle. So that's why the first step in finite volume method you have to integrate the equation using a finite volume. Because whatever the differential equation you have seen here, that is basically coming from this conservation principle only. And that conservation principle now we are applying to a finite volume size. So that's why it's named finite volume. So how do you get this finite volume conservation? By integrating this, the differential equation which is valid for infinite small size of the control volume. Now you have to integrate it for a finite volume size, then you will get the conservation for within a finite size of the volume because of our ease of computation. Because computation can only possible with finite precision. That means your special finite volume size should be finite, not infinite size, which you cannot capture using finite precision. No, it is just I have shown here the four control angles. It is up to you. It's the actual intensity distribution, let's say, quite arbitrary. Then you can create as many number of control angles as you wish to resemble this actual intensity. No, we are integrating over a small control angle like this. We are not integrating over the whole sphere. We are integrating over this small section. And then we are again integrating within this. Right? And that's why we are saying that within this small control angle, our photon intensity is constant. That is the primary feature of the finite. And how many number of control angles you need, that completely depends on your actual intensity distribution in different directions. No, that is the span. It's the domain size, angular domain size. Angular domain size, theta like polar angle, vary between 0 to pi, and azimuthal angle vary between 0 to 2 pi. And that have to be discrete. Like our special domain, you are discrete. So the two, let's say theta domain, you are dividing into 4 number of control angles. So that means pi by 4. And then if you divide the azimuthal domain into 4 number of control angles, then it will be 2 pi by 4. Like our domain, you are discretizing using our conventional CFD practice. The same thing we are doing with our angular domain. But here our angular domain is fixed. We cannot change because it is spherical, always spherical in nature. So our polar angle domain size is always pi, and our azimuthal angle domain size is always 2. Then it creates the full spherical intensity distribution like this one. Right. So, okay. And then the first step is to integrate this RT for a finite size control angle, because this is the concept of control angle now developed. Earlier that has not been sensed using flux method. Now when the finite volume method has been developed, then these flux people thought that, oh, it is, we have already developed a finite volume method, but yes, we have assumed only 2 control angles. Right? So if you there are more number of control angles, then you can go for finite volume method. Right. Yes. For each control angle, we have to calculate those values of mu and direction depending on the number of because the span of this theta minus theta plus and phi minus phi plus will be different depending on the control angle size. Right? So that will be. And then for our, this is just shown for a simplified case like 1D system. So you can integrate this for a typical control angle delta omega L. L stands for our particular direction. That means control angle direction. And here what we are talking about is theta and phi. This has been shown here. This theta is measured from our positive z axis, which varies from 0 to pi. And phi is measured from positive x-axis, which is 0. Then it constitutes the full sphere. So then after integration, you can see that the direction cosine term is coming like this, dCz, whatever shown. So this dCz is nothing but our direction cosine part. So this direction cosine is calculated for a finite size control angle as this nz cap dot s cap ut. And what is this s cap direction? Somebody was asking s. So this s is this one, the direction of travel of the photon. So in our Cartesian system, we can show like sin theta cos phi ex, then sin theta sin phi ey, then cos theta ez. This is our standard convention in finite method. We take it, but it is up to you because we have measure our theta from positive z axis and phi from positive x axis. That's what this is. Okay. So remember, that's why I am emphasizing here radiation is always 3-dimensional. Although I am talking about 1D system, this 1D only refers to spatial domain, not angular, because angular is always 3. So that we have to be taken care. So this is the direction cosine that you can calculate like this. So that constitutes our angular quadrature sets in DON, what you said. But in DON, you have to calculate and satisfy certain moment principle. But here in principle, you have generated only control angles, and depending on your control angle size, your weights can be different, which is nothing but your direction cosine. Is it? So, and for our one-dimensional system, we take Ez is Ez direction. We can take, that means whenever we are talking about 1D system in RT means radiation, that means along z direction will consider. And for 2-dimensional system, we take S1, that means Ex. And for 3-dimensional, all 3 components. Then our then second part, later on this has been linearized. So this linearization principle is done by Patanka group. So my advisor my PhD advisor have developed this linearized form of the RT during his PhD tenure at University of Minnesota. So this is something very interesting to see that the extinction coefficient, what you see here, this linearization is actually required because of this inscription, and that creates the major trouble for solving this equation or handling this equation. If this would not have been there, it would have been much easier to handle. So this here, whenever you are talking about, let's say I want to know my photon intensity in a particular direction. So when I calculate the in-scattering part, that direction is also there. But I am not sure what is my intensity in this direction. So then how do I calculate this? So that's why this my advisor, what he did, he splitted this part. He splitted this part into two parts. One is this modified extinction coefficient, another is modified source term, right? So earlier it was only source term. Now it has been split into two parts. Then in this modified source term, this direction of interest in our chosen direction is not present. Then it is very easy to solve it numerically because you do not have to guess many intensities. Otherwise you have to guess it and then again recalculate. So it consumes a lot of iterations and computational time also increases. So that should be our primary focus, and even Padankar always says that we must minimize the computational cost. Then only things can be realized. Otherwise you can create complex problems very easy but very difficult to simplify. So that's why we must ensure that it consumes less iterations, less computational cost, based on which we can get good results. That should be our primary objective. So what it does actually, this is then our linearized RT can be looking like this. So there is again a transient term, and there is a cluster, and there is a attenuation and augmentation. So this is the modified source term. Now this modified source term does not include the component L. You can see this earlier if you see the previous slide. So this, it is exclusively written L prime not equal to L. So this S and L component does not consider. So then you do not have to guess the source term. Right? That is the primary advantage. And the advantages of linearization is that one of the very important advantage here is that the effective optical depth reduces. Because although our physical dimension we are discretizing, but in radiation problems it is actually the optical dimension. That means the extinction coefficient times the physical dimension of the problem. So this beta into that physical dimension is the optical dimension. So since your beta is now reduces, you can see that this beta is now smaller than the actual beta. Our modified beta is now smaller than the original beta, so our optical dimension is reducing. So then what is our advantage? The fewer control values for discretizing the data, because now domain size means reduces. Although the physical dimension is there, but optical dimension reduces. So then you need fewer number of control volumes to get it, and then computation is faster. So it reduces our computational cost. So that is one of the very important advantage. And faster convergence because less gas intensity requirement for computational intensity. Because now this S and L does not include the L component, what we are looking for finding intensity either. Then our FEM formulation again is based on conservation principle. So we have to integrate it for a finite size of the control volume. So that has been done here. And to find then the second term, in order to simplify this second term, we utilize this divergence theorem. Then it can be written like this, and the transient term integration can be reduced to this. Okay, and then our flux term simplification, like after applying the Gauss divergence theorem, it can be represented like this. So this is, and then finally you can get attenuation documents simplification. Means what we are saying, whatever average value, because all these values what you see, like that I and S and beta, this P refers to the average value we are storing at the center of the cell, so that we will get good accuracy. It is basically the region where we are storing at the center is that it is second order accurate, so good accuracy you can get in your array. So this average value we are storing it at the center of the cell and then simplified it. And similarly, we have discrete RT, full discrete RT can be written like this. Then we have a special grid for a structured grid, it is looking like this. So we have a boundary grids are also there based on the character approach. We have a zero control volume at the boundary to handle the boundary condition much more effectively. And then we have an unstructured grid also there, and then you have angular space, whatever. So because that is always fixed, the span of theta and phi. That means phi and 2. And then we have control angles, control volume, standard nomenclature of the control volume for a 2D control volume has been shown here, like north, west, north, south, east, west. Okay, similarly you have a control angle size is also there, and then you have a control angles in your spatial domain looking like this, just like a conical shape, whatever I have shown. So each cone represents a control angle, and in a particular control angle intensity is and that is the average intensity coming out of this component, center of the component. So then the finite 2D, two-dimensional finite volume discrete equation now can be written like this form. So whatever direction function you see, these are all angular quadrature sets in discrete coordinate class. Then our modified extension coefficient and modified source term. And then while solving this equation, because we have so many unknown terms are there, so what we do, a step scheme we use is very similar to our upward scheme in our convection diffusion problem, CFD problem. So that has been applied here. Means upstream value prevails. So like for this particular configuration, you can see that the facial intensity can be approximated with corresponding color. So for this IE east phase should be equal to IP because the upstream is E. And for this the upstream is W. And for this again the upstream is P. And for this upstream is S. Like this, we simplify this. So that's why so many simplifications have been done. And finally in standard form it is like this. So where other terms have been VNA. And then we do have a compact form of the RT also there, which can be solved very easily, irrespective of different directions. All the coefficients, remember, all the coefficients are not activated at a time, because depending on your direction, some coefficients addition, some coefficients eliminate. So that's why it is like okay. So this is the standard finite volume discrete compact form of the discrete equation, and how do we solve it? At each time step, an iterative method is used to solve the resulting set of equations. A marching order can be used, can be employed to efficiently solve the set of algebraic equations, because once you start from the boundary information is known to you. So you can carry on based on the upstream value and go on computing the whole domain. TDMM, which is quite popular in solving CFD problem, that is tridiagonal matrix algorithm. It is not necessarily required here for solving the RT, for solving the finite volume based discrete RT equations, because it is simply based on match. So once you match from the boundary, all the values are known. So you do not need any explicit methodology for solving the discrete set of equations, unlike the case with CFD TD. So that is the slant advantage. And then coming to our radiation other mode of heat transfer, how we can handle. This is our conduction plus radiation example has been shown here. Professor Kumar was showing you the radiation source term. So that radiation source term is here. This is your radiation source. So how do you evaluate this radiation source? This radiation source in transient format can be written like this. But of course, remember this term is quite valid when you are going for very ultra short time scale. Otherwise, this is no significance. So simply this del dot U equal to kappa, which is the absorption coefficient, into A by IB. IB is the black body intensity minus G is the irradiation term. So why negative? Because it is looking like what you can say here. It is the conduction term. Like if you see the conduction term in terms of conduction, this will be nothing but minus del dot QC. This one. So now the Q is, because it is conduction plus radiation, so Q is QC plus V1. So actually it is minus del dot QC plus V1. So del dot QC minus del dot QC is this, just on Fourier law, and this minus del dot QL is split. So in order to solve this transport equation, we need the radiation information now. So that radiation information can be obtained. Radiation information in the sense, what is unknown here is the G. The G is the unknown term, because G can only be obtained when you have a intensity field everywhere inside the room. Because G is the irradiation, which is calculated integral of I d omega. Okay, over the whole sphere. So then, remember G does not depend on direction. G only depends on spatial location. Because G is the contributory effect of intensity from all the directions in a given spatial location. So that's why first you have to calculate this G, then only you can find this. And that you can put it over here to find this temperature and the temperature here. So then you can find the temperature inside the medium. Like in your combustion model, when radiation is also included, this part needs to be done. So first you have to solve for the RT as we have discussed using finite volume method. Once your RT is solved, your intensity distribution is known at every location inside the domain. Then the G value also known spatially everywhere. So once this is solved, you can find this divergence of radiation. So then you can put it as a source term, and this source term you take it to the standard linearized form Sc plus Sp5, and then you can find temperature maximum Hg. So that is the standard practice we follow. Similarly, if you go for convection radiation along with the phase change also, that we are now working on it, how radiation affects the phase change. So then you have a convection term is also there. Like in our convection diffusion equation, I have shown you at the very beginning slides. So there is a convection term, so that can be included. Then you can get it. So there is no more change. Conduction radiation and conduction convection radiation. Only you have to calculate this. Okay. And then rest of the things are quite known. Okay. And this equation can be solved using conventional CFD techniques. Those who are not exposed to CFD, of course, they may be new to that, but of course time is a constant. so we cannot discuss much more about it. But if you need it, I have the solution methodology for conventional CFD. That I will get it. That will be fine. Okay, that's all from my side. So our formal technical session now over. So then
Alright, thank you all for pushing through this 5-day gyms, 5-day workshop. So,
all my team, I am tired. So many technical sessions.